Tacoma Narrows Bridge of Washington on the morning of November 7, 1940, just after 4 months of opening, suffered a collapse in a wind of about 42 miles per hour. The span of the bridge was 840 meters long. It was called Galloping Gertie and it was a landmark failure in engineering history. This bridge was built at a cost of whopping 6 million US dollar, and at that time it was third largest suspension bridge. So what makes a concrete and steel structure so stiff, wobble like a jelly under a mere wind speed of 42 miles per hour? In this video, let us try to find some answers. To start with, we need to understand the basic mathematics behind it. A system can be defined as dynamic system when acceleration cannot be neglected. In such case, the product of mass and acceleration gives us the force. Now, force in a body which has undergone some deformation can also be defined as the product of stiffness with the deformation, giving us the force. Then there is a third type of force that is called damping force. Now, damping is the internal property of material to resist vibration. Now, in any dynamic system where an external force has been applied, can be defined by using these three forces.
This equation is applicable to a single degree of freedom system or a multi-degree of freedom system using matrices. And these system of equations can be solved, and it is called eigenanalysis. Solving these equations, we get different lambdas, where the number of lambdas are equal to the number of degree of freedoms. Suppose we have 3 degree of freedom, we will obtain 3 lambdas, and for n number of degree of freedom we obtain n number of lambdas. Apparently, each lambda corresponds to square of the frequency of vibration of the system. Now, when an external force is applied with same frequency as the natural system, resonance occurs. This results a huge energy surge, which can be detrimental for any system.
Something similar occurred on the morning of November 7, 1940, when the bridge experienced aeroelastic fluttering. This caused twisting of bridge in opposite direction because torsional mode was excited. To prevent recurrence of such an event, modal analysis is performed. Now, modal analysis, in contrast to quasi-static and dynamic analysis, it provides an overview of the limits of the response of a system. Another example is Mexico earthquake of 1985, where buildings having stories 6 to 15 collapsed, but buildings with story levels more than 15 stayed safe. Apparently, the frequency of earthquake accretion matched with the natural frequency of buildings having story levels between 6 to 15.
Engineers have been applying modal analysis to ensure safety of building structures, bridges, to mechanical structures and even aeroplanes. If you intend to understand the mathematics behind the eigenanalysis, I will highly recommend videos of Gilbertstein that are available in YouTube. Thank you for watching this video.